Hello? Yes? There, good. Yes, I suspect more people will come around about 10 o'clock when they're sure this lecture on physics is done. But thank you all for coming out for my favorite subject. We're going to talk this morning, as you see, about the distance starlight dilemma. And what is that exactly? Well, here we are in our little spiral galaxy away down here. And here's another galaxy, which goes under the fancy name of UGC 2885, which has been determined to be, am I coming across all right? Yes? Yeah? Which has been determined to be 232 million light years away, which, according to conventional wisdom, means that the light from that galaxy takes 232 million years to get here, because a light year is the time it takes, is the distance that light will travel in a year. So, if that's the case, how are we able to see this light if the Earth and the universe and everything was created only 6,000 years ago? That's a fairly legitimate question. To answer that, we need to solve Einstein's field equations for general relativity. Well, no, maybe we'll skip that bit. We need to talk about the fact that this discussion about cosmology and billions of years ago is really about history. And this gentleman, who actually studies cosmology, made that point very clearly when he said in an article in Science magazine that the goal of physics is to understand the basic dynamics of the universe. Cosmology, he says, is a bit different. The goal is to reconstruct the history of the universe. So, we have physics, the goal of which is to understand the dynamics of the universe. So we could call that operational science. That is, trying to understand how the universe operates. Cosmology, on the other hand, the goal is to reconstruct the history of the universe. So we might refer to that as historical science. Now this indicates fairly clearly that everything that kind of gets called science isn't the same. These two things are quite different. There's some other things that people may not appreciate about science, so I'm going to go through those because they're all very important when we're talking about these sciencey things. First off, science is all about doing repeatable experiments. This is affirmed by this gentleman, again, in an article in Science magazine. He says the basic tenet of science is you can do repeatable experiments. And I mean, if you think about it, the scientific method is all built around doing experiments. Now, in fact, this is the central bit of a somewhat larger quotation by this fellow. He says, cosmology may look like a science, but it isn't a science. A basic tenet of science is you can do repeatable experiments, and you can't do that in cosmology. Okay, so we'll go back to this picture. Under operational science, we can say there you can do repeatable experiments. However, in cosmology and other historical sciences, you can't do repeatable experiments. Continuing on, contrary to popular opinion, data don't actually speak for themselves. Now this comes from maybe not what most people would consider to be a scientist, but he's got his PhD in economics, so he does a lot of data manipulation. And he says data cannot speak for themselves. They have to be interpreted through a theoretical model. Some correlations that you see are spurious, that is, they don't really exist, and some are not. Extracting inferences from about causality, A causes B, requires an understanding of the theory, statistics, and how the data were collected. So putting that back on this diagram then, that actually applies to both types of science. That the data don't speak for themselves, they need to be interpreted. For that you need a theory, you need to do some speculation, and that speculation is based on presuppositions. And these presuppositions are really important. These are things that are just presumed to be true, but are never confirmed or tested or verified to be true. And they're really important. So we need to take a look at those. Mainstream presuppositions, or the presuppositions that underpin mainstream science, a fundamental one is the one of naturalism. That is, that nature is all that there is, so we need to explain everything using only what we can see to be happening in nature. Another name for it is materialism. That is, that matter is all that there is. So we have to explain everything based on the matter that we can see and the forces that interact between those bits of matter. Now that actually is underpinned by a more fundamental presupposition that usually gets overlooked, and that is that it's man that gets to define what's true. And man has defined naturalism to be truth, or materialism to be truth. That is, that's all there is. Nature is all that there is. There's no supernatural. From this, then, come a number of derivative presuppositions, if you like. That is, that the laws of physics are universal. They apply everywhere in the universe at all times. And that, obviously, you can't test other than in the limited region where we are and the limited time span that we exist. And from that, then, comes a number of other presuppositions that are particularly applicable to cosmology. One of these is the cosmological principle, and that basically is that the universe is homogeneous. It doesn't matter where you are in the universe, it kind of is the same. Now, it's obviously on a big scale, because there's obviously some significant inhomogeneity in the solar system. We got the sun, and then we got the planets and all that. But if you look at a big enough volume of space and another big enough volume of space, it's basically the same, so they say. And that it's isotropic. Doesn't matter which direction you look in, it's the same in all directions. They also say that it's finite and unbounded. That is, it's not infinite, but it doesn't have any edges. Huh? How does that work? Well, think of the surface of an orange, right? The surface of an orange is finite, right? But it doesn't have any edges. So that's kind of the idea behind that presupposition. And then there's the Copernican Principle. And that is that there is no preferred observational point. And this is applied because it's intended to try and avoid the trap into which people fell pre-Copernicus, that the Earth was the center of everything. That was Aristotle's philosophical position that led him to the geocentric model of the universe. So this has been imposed on the interpretation of the data. There's no way you can actually prove that. From a biblical perspective, we have a different set of presuppositions. We start with that God defines what's true, which means that the Word of God is true, which means that the creation account is true, which means that the universe started as water with the earth near the center. It was all done in 6 24-hour days, and all that happened about 6,000 years ago. Now, because of the Bible, we can also assume that the laws of physics are universal and over time. They're constant over time. And that's because the Bible tells us that God is a constant. He's not changing. So since the laws of physics are the means by which the universe that he constructed actually works, or if you like, the way he upholds the universe, we can conclude that they also are constant. But there's an exception, and that is when they are augmented by God's direct action. Now, this isn't a license for the God of the gaps approach, which is, well, if I don't understand how something works, well, that's just the way God did it. But it does apply to the miracles that are described in the Bible. Those are historic events. And when they are not consistent with the laws of physics as we know them, then we can conclude that that was God actually intervening. Now, to give you an idea of the impact that these presuppositions can have, touched the wrong place. Consider the evidence being the 747, and consider trying to construct a story, an explanation of how the 747 came into being. Now, if you don't constrain the answers you're allowed to have by imposing some presupposition, it's pretty obviously it was designed, right? But if you say you have to construct a story about how it came into existence using only naturalism, then you're forced to come up with some explanation, some story whereby it happened by accident, because that's the only option that you have. It doesn't make the answer right. It's the only answer that you have because of the presupposition. So when constructing, particularly when constructing stories in historical science about origins, these presuppositions are really important. And I think it's the same is true of the history of the universe, origin and history of the universe. If you don't impose any presuppositions, it's pretty obviously it was designed. But if you say no, you have to explain it naturalistically, then you have to come up with an answer that it happened by accident. Okay, with that as background, let's now look at the secular history, which is also known as the Big Bang, which is also known as the lambda cold dark matter model. Cold dark matter model, Big Bang. NASA's put together this very interesting pictorial representation of the origin and history of the universe. They say it happened, according to the Big Bang, they say it happened with a quantum fluctuation in which energy from the quantum vacuum field was transformed by a fluctuation into real energy and matter in real space-time. And it was all constrained to a very small volume of space. They called it a singularity. It was so small, so we have the entire mass energy of the universe contained in a pinpoint, if you like. And it obviously isn't at the moment. So the next step in the process was a period of what they call cosmic inflation, when the universe expanded by a huge volume in a very, very short period of time, and we'll discuss it more later, until it got out to a very large volume. But at this time, it was still what they called a plasma, very hot, so no light was escaping, and it took some 400,000 years for it to cool down to the point where it could, electrons and protons and things could recombine, and light could actually escape. And that's what's referred to as the cosmic microwave background radiation, the stuff that we see, which I'll also talk about later in a minute. Then there was a period of what they call the dark ages, because we don't have any stars yet. We only have hydrogen and a bit of helium and even a smaller bit of lithium. And it took some time to form those stars. These big gas clouds had to collapse under gravity and form a star, which then burned by nuclear fission to use up whatever hydrogen it had, and then it would explode, and in the explosion would create some heavier elements, and then emit 4 more gas clouds, and then we'd go through this cycle 2 or 3 times until we finally got the material with the really heavier elements at the upper end of the periodic table, from which we could then start to make the planets. Then we make the planets, or we put stars together in galaxies first, and then we make the planets. And in that sense, our sun is thought, or is said to have appeared at about this point in time. This is time along the axis this way, with each one of those lines being 1 billion years. So it happened about there, and according to the Big Bang, the Earth happened a little bit after, and the Moon happened a little bit after that. So then we have this expansion going on, slower than the initial cosmic inflation, but the expansion going on for something like 13.7 billion years. And recently, they've made some measurements that have been interpreted to mean that the expansion is actually accelerating. So we now have this supposed accelerating expansion to account for. Excuse me, now one of the issue we're going to be talking about is this distant starlight dilemma. Suppose there was a star that was formed way back here, and we are now over here with the Earth on the right-hand side. Sorry, that's over your right-hand side. And the starlight comes from the star, and it comes to the Earth, and we see it. And you'll see I've drawn on here that it starts out white, and when it gets to the Earth, it's red. It appears reddish, or more reddish than it was when it started. That's referred to as this thing called the redshift. If you look at the spectrum from the sun and put it through a prism, you get this sort of thing. And you can see superimposed on the color spectrum, there are some dark lines. Those are absorption lines from certain elements that absorb the energy that's in that spectrum that's coming from the light source behind it. And these absorption lines are indicative of particular elements. So hydrogen has a set of absorption lines, helium has a set of absorption lines, etc. And they have specific ratios, those lines. It depends on the electron orbits. Now, if you put the light from a distant galaxy through a spectrum, or through one of those things, prism, it also divides into light, and it also shows these absorption lines, but they're all shifted towards the red end of the spectrum. Now, this is typically indicative that the source is moving away, that the wavelength is elongated, because between each little crest in the wavelength, the source moves a little bit further away from you. So it's been interpreted as indicating that the universe is expanding. And they calculate this redshift as being approximately the velocity of expansion divided by the speed of light. And they've noticed that things that they've determined to be further away from the Earth have a higher redshift, and therefore the things further away are receding from us faster, which sort of makes sense, right? I mean, if things have been going on for a period of time, the things that have been happening faster will be further away from us. Now, a lot of this redshift isn't actually from the in the Big Bang interpretation, isn't actually from the motion of the galaxy. It's from what they refer to as the stretching of space, or the cosmological redshift. So with this space expanding, when the light is emitted, as it travels through space at this constant velocity, it takes time to get to different regions of space. And when it gets to another region of space, that part of space has stretched a little bit more, and then a little bit more. So it has to travel a little bit further each time. So its wavelength has to increase. So if you think of it as, if you think of that sine wave being stuck on a piece of rubber paper, then you stretch it, and the wavelength gets longer. So it gets shifted towards the red end of the spectrum. Okay, so it looks like normal recessional velocity, but in the Big Bang, it's interpreted as being an expansion of space. That then leads us to this thing called Hubble's law, which was developed by Edwin Hubble, after whom they've named this telescope. And it looks like this. He measured redshifts and distances for a whole lot of different objects in the sky, and he plotted them on a graph, and he found out they looked like this. This is redshift over here, and this is distance from the Earth, measured in millions of light years. Notice the scale there. And this, of course, is recessional speed, as we've just talked about. It's the speed at which the object is moving away from us, however that has happened. And he saw, look at that, nice straight line. Isn't that wonderful? So we can use this as an advice. But it's not quite as simple as that. There's a group of stars called the Virgo, or galaxies called the Virgo Cluster, and they don't fit nicely on the line. There's another galaxy out here that fits nicely on the line, but there's a quasar that's been ejected from the galaxy towards Earth. And they can tell that because of the evidence of a filament that's connecting the two, like a gaseous filament that's connecting the two. It has a measured redshift of 2, which on this plot would put it at 21 billion light years from Earth, but it's not. So this relationship of redshift and distance is not necessarily as definitive as Hubble's law would have us believe. Well, one of the issues might be that the distances aren't actually correct. So how do they actually measure distances? Well, the first method is by simple geometry. So if we have a star here and they want to measure the distance to the star, they take an angle sighting between the line of sight to the sun and the line of sight to the stars at one time in the Earth's orbit, and then they wait until it gets around on the other side and they do the same thing, and then knowing this distance, you can use simple geometry to calculate the distance. It's called parallax. And the units that they use, unit of distance is a parsec, which corresponds to the distance when this angle is 1 arc second. And you may have heard in the various science fiction movies, they talk about megaparsecs. Well, that's just 1,000,000 parsecs. And a parsec is 3.26 light years, so a megaparsec is 3.26 million light years. Now, that'll only work out to a certain distance, and then the angle gets too small to actually measure accurately. So what they've done then, they've effectively built a ladder. So they have one measurement, like parallax, that'll work out to a particular distance, and then a star near the end of that distance, they measure the distance to it or determine the distance to it by another mechanism that is more theoretical and depends on a bunch of assumptions, but it incorporates measurements of certain parameters. And then if they can get those to line up, right, then they can use that to extend out to another distance. Okay, so parallax is good out to about, with Earth-based telescopes, out to about, what's that say, 326 light years? And if you use space-based telescopes, you can go out to just over 3,000 light years. And if you get really clever, using the Hubble telescope with some post-processing, you can go out to about 75,000 light years. So that's all sort of still within, if you like, the biblical time frame, more or less. The next method is actually a collection of different methods. There are a number of different methods that they can use that extend the distance out a little bit further. And then there's a third one, and a fourth one, and then there's Hubble's law, which is used to relate redshift to distance. So if you can't use any of these others, or even if you can, they'll use Hubble's law as a default. If you were to put these on an actual scale, it kind of looks like this. Parallax covers that distance. The next one covers this distance. The next one covers this distance. The supernova ones go out quite a ways, but they're pretty sparse. I mean, there are not a lot of those, so you can't use them very much. And Hubble's law, basically, they say, applies everywhere. Now, I mentioned the Virgo Cluster earlier. It actually sits at about here, which is too far away to use parallax. But they've used all of these others, and a couple more actually, to measure or estimate or determine. Now, measure isn't a good word because it implies, you got a tape measure and you can actually measure it. What they're doing is inferring how far away it is from various things that they do measure, like variation in intensity and all of that kind of stuff, and then using some theoretical models to calculate what the distance would be under that model. So they've used all of these different things, and they've got these different estimates with the uncertainties, as quoted, and if you put them on a graph, they look like this. So they're all kind of more or less the same. This one, if you were to take that as the value, it includes almost all of them within the uncertainties and the measurements. So all of this sounds pretty okay, right? I mean, if this was all you heard, you'd think, wow, this Big Bang stuff is pretty well established. It seems to be all hanging together and everything. However, the Bible says, we need to examine everything carefully and hold fast to that which is good. So let's look at this carefully. I'm going to use here quotations from secular scientists to indicate that the Big Bang is not everything that we are led to believe it is. Considering first the quantum fluctuation. But there's a very real problem in explaining how it all got started in the first place. You can't fudge this by appealing to quantum mechanics. Either there is nothing to begin with, in which case there is no quantum vacuum, no pre-geometric dust, no time in which anything can happen, no physical laws that can affect change from nothingness into somethingness, or there is something. In which case, that needs explaining. So the quantum fluctuation doesn't actually solve the problem of the origin of all of the mass and energy that's in the universe. The other issue with that account of the origins is that if we start with no matter, and then we have a quantum fluctuation, we should wind up with equal numbers of things called baryons and antibaryons. That is, matter and antimatter. But these two entities have this nasty habit of recombining instantly and reverting back to energy. And so you should have an equal amount of matter, an equal amount of antimatter, which should annihilate each other, and we go back to a state of no matter. But what we actually have, obviously, isn't that. Otherwise, we wouldn't be sitting here talking to each other. We start out with no matter, we have something, and we have baryons. And wherever they look in the universe, they only have matter. They don't see any antimatter. You can manufacture it in the lab, but it doesn't exist naturally. So this is referred to as the baryon asymmetry problem, and it's an unsolved problem in physics. Well, they do have a sort of solution. It's a mythical process called baryogenesis, which violates this law of conservation of baryons. So that's an exception to their rule that the laws of physics and the laws of physics apply everywhere all the time, except when it's inconvenient, I guess, and then they'll just invent something else. Then we have the issue of inflation. Now, it happened very quickly, 10 to the minus 32th of a second, if you can imagine that. The volume increased dramatically, 10 to the 78th. And if you understand what those numbers actually mean, could you please speak to me afterwards? I have real trouble trying to comprehend them. They have no idea what started it, no idea what would propel it. It's got to be an anti-gravity force of some kind, because it's got to take all this material that's scrunched right up and spread it out. They don't know what stopped it. There's no experimental evidence for it, and it's not testable. Doesn't sound like anything very scientific to me. So why is it there? Well, it was introduced in around 1980 to solve a number of problems. One of them is the horizon problem, which I'll talk about in a minute. But there were a couple of others. Now, in 2015, they had a 50th anniversary conference, or 50th anniversary of the discovery of the cosmic microwave background radiation, in which this guy, very big name in the field, said inflation isn't falsifiable, which is another characteristic that theories should have. They should be able to be proved falsifiable. It's falsified. So in his opinion, inflation has been falsified. So it shouldn't be there. But without it, we got all these problems with the Big Bang. Okay, how about this cosmic microwave background radiation? That was discovered in 1965 by these two guys who were doing experiments with satellite communication and couldn't get their equipment to work properly because there was too much background noise. After spending a lot of time trying to fix the equipment, they finally concluded, well, this was a real signal. It wasn't noise. So they measured it. It looked like this. And it's what's referred to as a spectrum of black-body radiation that perfectly fits the theory for a black-body radiator at a temperature of 2.725 degrees Kelvin. Now, this was concluded to be this product of the Big Bang, so it's been very extensively studied. They send up satellites which look around space and effectively measure the temperature. They measure the wavelength of the radiation that's coming in, but they decode that into temperature, and they get things that look like this, where red is hot and green and blue are colder. Green is colder and blue is cold, lower temperature. Now, obviously, this isn't very cold because there's this really hot bar. That's the stars in the Milky Way that are in the front. So it's not background radiation, that's foreground radiation. So you got to get rid of that. And the way they do that is to make this same measurement in a whole bunch of different frequency bands and then run them through a program that is to simulate what they think it should look like and subtract them all off, and they get something like that. And what they found out was it's uniform in all directions to 1 part in at least 100,000. Now this creates a bit of a problem because the only way you can make temperatures uniform in space is by radiative heat transfer. That's by light moving from one place to another, or thermal energy moving by light from one place to another, right? So to get both opposite sides of the universe in thermal equilibrium would take a very long time. And there hasn't been enough time for that. In fact, they say that this occurred about 400,000 years after the Big Bang, in which case you could only equalize a volume of space about that big, which means you could make all of that volume of space the same temperature, and you could make all that volume of space the same temperature, but you couldn't ensure that both those volumes were the same temperature. So that's what I say is the horizon problem, and the solution for that is inflation. So if inflation goes away, then there's this problem. Next, we have the dark ages and star formation. This fellow says, the truth is, we don't understand star formation in a fundamental level. The formation of stars is one of the most fundamental problems in astrophysics, as it underlies many other questions on scales from the formation of galaxies to the formation of the solar system. No current model can reproduce all the observations. And then this guy, who is quite a well-known spokesperson for the evolutionary worldview, says the scary part is that if none of us knew in advance that stars exist, frontline research would offer plenty of convincing reasons why stars could never form. And he's actually got a much longer quote than that. So this whole idea of star formation that I went through, that actually has to happen 3 times, highly questionable. Of course, that means that if you can't make stars, you're going to have some trouble making galaxies, and that's what they say. We have no direct evidence of how galaxies were formed, whether they were formed from aggregations of smaller units or from subdivisions of larger ones. We don't understand how a single star forms, yet we want to understand how 10 billion stars form. Okay, well then let's overlook that for a minute and let's move on to planets. The other problem with galaxy formation is that they've looked way back in time, in distance in time, and they've seen really nice, perfectly formed galaxies at a time when there should be only stars. We expected to find basically 0 massive galaxies beyond about 9 billion years because theoretical models predict that massive galaxies form last. Instead, we found highly developed galaxies that just should not be there, but are. Fool. Right, well, now let's move on to planets. Well, the story for planet formation, like Earth and Venus and Mars, the rocky planets, is that you start out with this disk of what they call a protoplanetary disk, which is basically a bunch of dust and a bunch of gas and dust modules. That's gas and dust bits. And they're all going around a big circle, right? They're a big disk that's going around. And the gas collapses under gravity to form the star, and the dust bits bang into each other and stick together and get bigger and bigger and bigger and bigger and bigger until finally, voila, they form a planet. However, the pebbles, this guy says, are in limbo. He goes through a long analysis about how they might stick together or not, how they interact with each other, and he says they're in limbo. They are too massive for one force, the electrostatic force, to get them to stick, and they're too massive, they're not massive enough for another force, gravity, to pull them together. So they're not sticking, and either by electrostatic attraction or by gravitational attraction. Then another fellow says these small objects, solid objects that small, would have been buffeted around by the pressure of the gas surrounding them and sent spiraling into the sun long before they could get together. Okay, so Earth's a little bit dicey. Then we go on to the further ones out, gas planet formation, where it's the same sort of thing. The gas is supposed to condense into a small thing, and then it, as that planetesimal, if you like, sweeps around the sun, it just kind of collects, sweeps up gas and grows and grows and grows and grows. However, computer simulations have never explained how planets as big as the two gas giants could form so far from the sun. Bodies orbited so slowly in the outer parts of the solar system that the slow process of gravitational accretion would need more time than the age of the solar system to form bodies with that size. Okay, so we got a problem with forming the sun, the Earth, the other planets, and Jupiter and Uranus. So what's left? Well, this dark energy, or this accelerated expansion that led them to conclude that there's some dark energy existing. However, when astronomers suddenly realized that the universe was not merely expanding, but accelerating in its expansion, most of them concluded that some otherwise undetectable anti-gravital force, a dark energy, was shoving apart galaxies. An alternative possibility, however, can explain the observations as a fluke of cosmological geometry. It avoids invoking dark energy as an ad hoc cause, but at the price of throwing out the Copernican Principle. Roughly speaking, it puts Earth, or at least our galaxy, back at the center of the observable universe. But you can't have that, right? That's too much like the Bible. One other observation that is proving a little difficult for the Big Bang folks is the fact that if you look at these spiral galaxies that are rotating, according to the classical physics, the stars at the center should be rotating faster than the stars in the arms. It's a conservation of angular momentum, okay? So these ones should be rotating quickly, and these ones should be rotating slowly. But in fact, when you look at the measurements, they're all going at about the same speed. It looks like about this. There's the observed ones, and I'll just put a black line in there so you can see it better. And these are the predicted velocities according to the conservation of angular momentum. So the solution to that problem is magic dark matter stuff. That it doesn't interact, you can't see it, doesn't emit any light, doesn't emit anything. The only way it interacts is gravitationally, and it's just the right amount and in just the right distribution to provide just the right amount of additional gravitational energy to keep these stars rotating. So, if we review that quickly, quantum fluctuation doesn't seem to explain anything. Inflation's been falsified. This doesn't hang together. Where am I going? The star formation doesn't work. Galaxy formation doesn't work. Planet formation doesn't work. And the dark matter isn't required, or dark energy isn't required to do this accelerated expansion. You just need to change the geometry. And we've got this problem with these rotating spiral arms. So that really questions this whole story about the Big Bang. All right, so let's now look at the biblical history. And I'm sure you're all very conversant with this, so I'll just click through it pretty quickly. In the beginning, God created the heavens and the earth. There we are. And it says, and the earth was formless and void, and the Spirit of God was moving over the surface of the waters. here we are, the universe, so the universe obviously begins as water. And there's some number of things that we can infer from this by logic. That is, that at this point, atoms exist. It's water. We got H2O. So we then, therefore, can conclude that we have neutrons, protons, and electrons are in existence. That implies that we have the strong nuclear force and the electromagnetic force and quantum mechanics. Okay, so when God did this apparently simple thing, he did all of that. Right? Molecules also exist. Of course, that's part of the electromagnetic force. And gravity exists because we have mass, and gravity is the interaction of mass. So that means that the water that's there has been formed into a sphere, and it has a surface, because it actually said that there is surface to the water. All right, then God said, let there be an expanse in the midst of the waters, and let it separate the waters from the waters. Okay, so let's separate the waters from the waters. We got separate the waters which were above the expanse. Separate the waters which were below the expanse from the waters which were above the expanse. So we wound up here. And God called the expanse heaven, and there was evening and there was morning, a second day. Then God said, let the waters below the heavens be gathered together in one place, and let the dry land appear. And it was so. So now we've got the earth. Then he made some trees and stuff, which isn't germane to what we're talking about. And he says, then there was evening and morning, the third day. Then God said, let there be lights in the expanse of the heaven. And God made two great lights, the greater light to govern the day, and the lesser light to govern the night. Oh, and then, yes, almost as an afterthought, he made stars also. So we'll put some stars in. And then there was evening and morning, a fourth day. Now, it's interesting to note elsewhere in Psalms 148 that it says, praise him, sun and moon, praise him, all the stars of light, and the waters above the heavens. So when the psalmist wrote this, those waters were still there. Okay? All right, now the next thing I want to point out is that at various points in the Bible, it talks about God stretching out the heavens. It was I who made the earth and created man upon it. I stretched out the heavens with my hands. When did this occur? Well, it could have occurred any time, but of particular interest, if we say on day 2, after God made the expanse, there would not be, or it could occur on day 2 after he created the expanse. It could occur on day 3 after the earth was made, or it could have occurred on day 4 after the moon, the sun, started up, or it could have occurred later. But these are the sort of significant breakpoints. But if it happened on either day 2 or day 3, there would not have been much likely impact on anything. So they're of marginal interest. But if it happened after day 4, or after the sun, the moon, and the stars had been made, it would, in fact, cause some observable impact, like this, right? Where then this waters above would be out at the edge of the observable universe, what we now know to be the edge of the observable universe. All right, so that's kind of the biblical account, the history. And then before we try and figure out how we can explain the distant starlight dilemma within this context, there are a couple other things we need to be aware of from a perspective of physics. And one is a rather odd thing about time. Time, as it turns out, does not pass at the same rate everywhere. Now, I've had kind of almost a lifetime of experience with this because time at my wife's place runs real different than time at my place. But they actually do, as it turns out, run at different rates in different places under different conditions. For example, they tick more slowly when they're in a stronger gravitational field. This comes from Einstein and his theory of general relativity. So if you have two atomic clocks, exactly the same clocks, one down at sea level and one up at the top of a mountain, they tick at different rate. So if you count seconds by the number of oscillations of atoms and things like that, they go at different rates. And this is significant enough, it's not very big, but it's significant enough that it's one of the things they have to take into account in your GPS navigation system, because GPS works with clocks, atomic clocks on the ground and atomic clocks and satellites, and they tick differently. And so if you don't account for that, your navigation system goes all wonky. Now, a consequence of this are things called black holes. That's not a consequence of this, but black holes have an interesting consequence because of this. Black holes are areas of space where a largish amount of matter is concentrated in a relatively small volume of space, which produce a gravitational field that is so strong that nothing can escape, not even light, which is why it's called a black hole, right? Because you don't see anything. So, like I show in the picture, if you got the black hole here, you don't see any space behind it. It's just black. And this has a thing called the event horizon. And the event horizon is the radius around the black hole where if anything gets to the event horizon, it just disappears into the black hole and never comes out again. Now, because of this very strong gravitational field, and what we just learned, it has an impact on clocks. And as it sucks in matter, it actually gets bigger, right? The event horizon of the black hole expands because it depends on how much matter is actually inside the black hole. So it'll get bigger and bigger. Now, as I say, it has an impact on the passage of time. If you had a clock way far away from the black hole, so it's not experiencing any gravitational effect from the black hole, it'll run at the normal rate. As it gets closer to the black hole, it'll start ticking more slowly, until when it gets to the edge, to the event horizon, it actually appears to stop. If you're watching the clock as it goes in, it'll actually appear to stop. Now, in physics, in the solution to those equations that I showed earlier, it allows for things called white holes. And, not surprisingly, they're the opposite of black holes. Instead of starting small and accreting matter and getting bigger, white holes start big and expel matter and get smaller. And rather than clocks running very slowly at the event horizon, they run very fast at the event horizon. And that rate depends on how much matter is still inside the black hole, or inside the white hole. So as the white hole shrinks, the clocks run more and more slowly until when it disappears, the clocks are running at the normal rate. Okay, so with this background, we can now look at not one, not two, but actually 5 different possible ways to explain the distant starlight dilemma. I call them the white hole cosmology, new physics cosmology, timeless zone cosmology, creation time coordinates, and the asynchronous simultaneity convention. And you can see they're all based more or less on Einstein's physics. We'll talk about them. Okay, the white hole cosmology is something that was put forward by Dr. Russell Humphrey, and basically his proposal was that when God created the universe, he created it as a white hole, right? So that with just outside the waters above, which contained all of the mass energy of the universe, the clocks would be running, or right at that event horizon, the clocks would be running very fast. But because it's a white hole, matter would be expelled from the white hole, and the white hole would shrink, and the clocks would run more and more slowly until it disappeared at the Earth and went away. Which would mean that the consequence of that is that way out here, billions of years had passed by the clocks that were associated with that point in space, while only a few seconds, perhaps, were passing on Earth. So during day 4, all of that happening provided the time for all of the light from those distant galaxies to get to the Earth and appear on day 4. Okay? Next one, the new physics cosmology. This incorporates the I stretched out the heavens idea, right? It's put forward by Dr. John Hartnett, who worked on it using a new physics called cosmological special relativity that was proposed by a Dr. Moshe Carmeli. He developed the equations, and what those equations did was they extended Einstein's description of space from 4 dimensions to 5 dimensions in the same sort of way that Einstein had extended Newton's description of space from 3 dimensions to 4 dimensions. And the 5th dimension was velocity. Now, Dr. Hartnett solved those equations, taking into account the stretching out of the heavens. Because when you stretch out the heavens, because of its velocity component, you create an acceleration. And it turns out, by solving these equations under those considerations, that clocks run at a different rate depending on the acceleration they experience. So if we go back to this picture, the Earth, being at the center of this whole exercise, doesn't experience any acceleration. So whereas this galaxy or star would experience a little bit of acceleration. It doesn't have to go very far, so you don't have to get it going very fast to get it there. But this one would experience a very high rate of acceleration. Now, John worked out, whoops, I hit the wrong side of it again. John worked out that the relationship between a time interval, a tick on an Earth-based clock, and a tick on a clock associated with one of those galaxies that's undergoing acceleration would be expressed by this simple equation, where this is the amount of acceleration it would experience. So what you can see from this is that if the galaxy receives a very high acceleration, its clock ticks much, much faster than the Earth clock, and a lot of time passes on that galaxy when very little time passes on the Earth. So back here, the Earth would clocks tick at a normal rate. These other clocks tick at higher rates depending on the amount of acceleration that's experienced. One of the nice things about Dr. Hartnett's model is that it explains these apparently anomalous rotational velocities of the stars in the spiral arms of the galaxies, these being the observed ones, right? This green one is the one you expect according to Newton's laws, but the red ones, the red line, the dashed line, is what is predicted by Carmeli's equations. So this Carmeli's cosmology explains the way spiral galaxies are rotating without any requirement for dark matter. Okay, now to the timeless zone cosmology. This goes back to Dr. Humphreys again. He's kind of into this cosmology stuff. In this case, we need to think of space-time, or space, I guess, space, as a trampoline, right? The fabric on a trampoline. And when you put like a big bowling ball or a big weight or something in the middle of the trampoline, it deforms the trampoline, right? So his view is that when God first made the universe, when we were at the stage of having the earth and the waters above, we had a scenario like this. Right, so we have the Earth at the center, and then we have a ring of waters above at some distance away from it, which is depressing space in this manner. If you look at it directly from the side, it looks like this. And his premise was that a combination of the Earth and the waters above provided enough mass so that the gravitational field, the gravitational potential energy, the amount of depression in the fabric of the trampoline, space trampoline, was such that it went down to a point where if it went any further, that's the dashed line below that you would be like inside a black hole. So time would have apparently stopped. So he referred to that as the timeless zone. So this would be the expanse, and then down below this line, there would be no time. It's a timeless zone. Then he said, okay, now we've got that done. God now creates the stars and galaxies in a wave starting from the Earth and moving outwards. And here's what would happen when that happens. I hope. Takes a bit to get started. There we go. Okay, so now he's adding more mass. So with the stars and galaxies, so what happens is that everything sinks down into the timeless zone. Then what happens is, when he's all done, he stretches it and pulls the fabric of space back up, so all the stars pop out of the timeless zone and start emitting light that starts traveling towards Earth, and Earth is still in the timeless zone. Then Earth finally pops out of the timeless zone just in time, to see the light as it arrives from the distant stars. Okay, so the fuchsia ball, or whatever that color is the timeless zone, or the outside of the timeless zone, and it is shrinking. Things keep popping out and starting to emit until finally there's the Earth. All right, so that's that one. The next one is this idea of creation time coordinates. And to do that, we've got to get into a little bit about how they represent space-time in diagrams. They're called Minkowski diagrams. They're really just like graphs. You do X, Y. Normally, when you do a graph, and sometimes you draw Z coming out. Well, in this case, you got the X, Y, Z, but we only show X here. And the other axis is a time axis. And to make it, so we've got a spatial axis, X, and we got a time axis. But to put it into the same units as the spatial axis, it's not just time, which is seconds, it's time multiplied by the velocity of light, which transforms it to spatial dimensions. Meters per second times seconds gives you meters. So we have the speed of light and time. Then all of these other things in here are important. These are events that exist in space-time. So they exist somewhere in space and they happened at some point in time. This thing B, this line B, is what's called a world line of a particle moving through space in time, right? So it has a time coordinate and a space coordinate. And this line in particular is what's is called a light line. It's the line that light would travel in space. And it's at 45 degrees because space and because time and the space and time, because you got the speed of light multiplied by time, it goes off at that particular angle. Now, we have the observer at the center of the coordinate system. And the axis, the CT axis, is the observer's world line. It's how the observer moves through space. The coordinate system is always centered on the observer, so his spatial coordinate doesn't change. Only his time coordinate changes. And the x-axis represents a simultaneity convention. That's time is the same everywhere on that dimension. This then leads to the idea of light cones. And we have future light cones and past light cones. A future light cone is the volume of space that will receive light from the Earth at any time in the future. Okay, so light goes off in this dimension, and over time, it fills in a volume of space. Then we have past light cones. The past light cone is the volume of space from which, it's the volume of space from which light originating at any event can be seen at Earth. Right? So as long as there is that event C, for example, is inside that light cone, so its light from C can reach the Earth within that time, can travel across the amount of space it has to get to the Earth in that amount of time. Light from A and B, or light from A, can't. So we now have these future cones and past light cones, and if you put them on a three-dimensional plot, they look like this. And if you draw imaginary lines through this, if it's all inside both light cones, that's a time-like world line. It just wanders through space, but within the constraints of time. The ones on the edge of the cone are light-like world lines. That's the maximum deflection light can have. And if you go along on the horizontal plane, that's just a space-like curve. All right, with that kind of introduction then, this creation time coordinates kind of combines these light cones. Now in this picture, we have two sets of light cones, right? Oh, I should say first, creation time coordinates. In creation time coordinates, events are synchronous if they happen at the same time in this coordinate system. It's like we kind of have two different time measuring systems here on Earth, right? We have our local time. Oh, hey, let's not get confused with standard and daylight. Just take Eastern Standard Time. Then we have Greenwich Mean Time. Or more correctly, we have Coordinated Universal Time, which is based on Greenwich Mean Time. So we set our clocks by our local time, and if we want to interact with somebody in the UK, we adjust our time to figure out what time it is for them. But we could all use Greenwich Mean Time. And if we were to do that, then Their clock would say the same thing as our clock. So if you wanted to talk to them at 8 o'clock in the morning, you'd look at your clock and it's at 8 o'clock in the morning, so you'd call them up, you'd know they'd be at work, except it'd be dark here, right? So it's just a different way of measuring time that's maybe different than we're used to. In this case, what we're saying is this is like Greenwich Mean Time. It's the time on the Earth is whatever the time is everywhere in the universe. So what we have is, we have the Earth at the center. We have the light cone associated with the start of day 4 on the Earth. And then we have the light cones that are associated with the start of day 5 on the Earth, or the end of day 4. So the space-time between that is day 4, everywhere. It's day 4 on the Earth, and by definition, it's day 4 everywhere else. Okay? So this then becomes the hypersurface of the stars that were created on day 4. It's the hypersurface of anything on that surface will be in day 4 creation time coordinates. So here's a star over here, emits its light, and it arrives at Earth on day 4. So that's their approach. So when basically it's what it's saying is when the Bible talks about day 4, it's using creation time coordinates. It's using a time measuring system that is based on the Earth clock convention. It would be like using Greenwich Mean Time to measure the time here. And in fact, armed forces do that, right? The armed forces always use coordinated universal time. They don't use local time to avoid confusion, right? It's the same time everywhere for everybody, no matter where they are. So it's not an unusual convention. Now, there is another one. To get to this other one, we need to understand that the speed of light is actually a convention. Consider two strikes of electricity that send light to an observer who happens to be positioned midway between where the two lightning strikes strike. If we were to calculate how long it took for the light to get from each of those lightning strikes to the person, to the observer, we'd come up with something like this. But Einstein, when he was developing his theory of relativity, pointed out that the assumption that light requires the same time to traverse the path from A to M as the path from B to M is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will to arrive at a definition of simultaneity. Okay, so the reason it's not a supposition or a hypothesis is that if it were those, you could test it. Right? That's what science does, right? It makes a hypothesis and then it tests the hypothesis. But you can't test it, and I'll get into that in a minute. So this is a convention, right? The speed of light in different directions, the one-way speed of light is a convention. And what Einstein chose was that light would have the same speed in all directions. It would be isotropic. And it's referred to as Einstein's simultaneity convention. And he did that so he could define what constitutes simultaneous events. Okay, so I mentioned that the reason it's not a hypothesis is that you can't measure the one-way speed of light. Here's an example of how people measure the speed of light. Over here we have a laser. It emits a pulse of light, travels down, hits the rotating mirror, goes up and hits the stationary mirror, and bounces back to the rotating mirror. Did I get there? Yes, okay. So then, in that length of time, between the first strike on the rotating mirror and the second strike on the rotating mirror has moved a little bit. So the return light goes down this pace, which is separated a few degrees from where it started. Excuse me. Now, if you know how fast the mirror is rotating, you can calculate the angle you would expect to see based on the time it takes to go back and forth between the rotating mirror and the stationary mirror. And if that distance of separation is length, you can calculate that this way. And if you put all of those into the equation, you can get this. So you can calculate c, the speed of light. Notice it depends on twice the length. So it's not a one-way speed, it's a two-way speed. It's from one mirror down to the other mirror and back again. And that comes from this equation up here. So you could just as easily say, well, I think when it goes from the rotating mirror when it hits it the first time down to the stationary mirror, it's actually going at an infinite speed. And when it comes back, it's going at a speed of c over 2. And if you put that into the equation, you get the same result. And you can't tell the difference, right? Because you can't measure the one-way speed of light. And it turns out, I mean, people have tried all kinds of different ways to measure the one-way speed of light, and it just can't be done. So now if we go back to these light cones and ask, what happens? Remember, the edges of the light cones are determined by the speed of light. So what happens then if we allow the speed of light to get increasingly larger? Well, that angle will increase until you wind up with not a light cone, but a light disk. So under this convention, anything in that light disk will appear instantly to the observer, the instant it happens. Now, the future light cone will have a somewhat different shape. It'll look like this. But by the time you get into the future, I mean, you can't measure it because it's a future light cone. It'll just be, it'll look the same as this, only further along. So if you go back to this diagram, which is kind of messy, I'm sorry, and assume that inbound speed of light, so we have an observer on the Earth, and light is coming at that observer, and you assume that inbound speed of light is infinite, and you can't tell that it isn't, then this is what day 4 looks like. It's the space-time disk between the start of the light cone on day 4 and the end of the light cone on day 4. Only it would be the start of a disk and the end of a disk. And you can put in the other days, 1, 2, 3. They look like that. So then overlaying the biblical account on top of that, you have day 1, this happens. Day 2, this happens. Day 3, this happens. And then in day 4, we have the sun, the moon, and the stars. And the light from the stars is immediately received at Earth because the speed of light is infinite. So it takes 0 time for it to get here. Then it goes out away from the observer at c over 2. Got it, right? So, those of you who were here last night will recognize these. This is kind of what these weekends are all about. It's equipping you so you will be able to either answer questions or demolish arguments. Well, what sort of questions? Well, what about the Big Bang? Okay, it doesn't seem to correspond with the Bible. Now, how can we see light from distant stars? Now, you can give them 5 different explanations for that, right? Right? Okay, good. Then, what sort of arguments? Oh, you know, the Big Bang proves that the Bible is wrong. So what are you going to say to that? How are you going to demolish that argument? Well, I've given you a certain amount of information with which you can do that. But those of you who were here last night have probably already forgotten about the Ebbinghaus forgetting curve. Those of you who weren't here last night, the fellow by the name of Ebbinghaus did some experiments to determine that we forget stuff really well. But we also know that if we want to remember more stuff, it helps to review. And the more times we review something, the more of it we will remember, and the less we will forget. And since I understand this kind of stuff is eminently forgettable, it really helps to have resources. And so I'd like to highlight a few that address this particular problem. The Answers book actually addresses a lot of questions, one of which is this issue of distant starlight. It has the answers to the 60 most frequently asked questions. Evolution's Achilles' heels is mostly about biology and evolution, biological evolution, but it does have a chapter on cosmology, which is very good, and it has an accompanying DVD or Blu-ray. And then specifically with respect to the topic here, there are these resources. Dismantling the Big Bang does exactly that. It's where a lot of the material came from about the problems with the Big Bang. Starlight, Time in the New Physics is Dr. Hartnett's book about his model. It also has an accompanying DVD. Light Years, No Problem is where I got those cool little computer graphic things for Dr. Humphrey's model. And then the distant starlight dilemma is a previous version of this talk, which doesn't have all of that last stuff. in it about creation time coordinates and asynchronous isotropy convention, but it covers most of the same material. And then there are quite a number of others out there that have to do with cosmology, which are excellent. And for those of you who weren't here last night, or even for those of you who were, I'd like to remind you about Creation Magazine. If you don't already have a subscription, that would be an excellent resource as well, because there are frequently articles in cosmology in here, most of them actually written by Dr. Hartnett. Also a lot on the web site by Dr. Hartnett. But in the end, getting equipped so we can do this is really the most important thing. So thank you. I'm sorry I ran over time. I got to learn to talk faster, or say less, or something. I think we're going to now have about a half-hour break. I think we'd probably like to get back about 10:30, so you can go out and collect all these resources and go and see the folks at the book table and be equipped. Thank you very much for your attention.